It's my pleasure today to invite Ryuji Takagi to give a talk on error mitigation for Horizon's Tech Talks at Horizon series. Ryuji did his PhD in MIT from 2015 to 2020 on quantum resource theories and made some very important contributions to the resource series of quantum channels. After that, he went and worked for the startup Kinesis for a little bit in Tokyo, and they concentrated on using error mitigation techniques to obtain some of the benefits of quantum computing, but to trade off some of the advantage you get in quantum computation against fitting the program to a near-term, noisy, intermediate-scale quantum device. So this work actually gave Ryuji an interest in error mitigation techniques, and more recently you've been working on the information theoretic characterization of error mitigation techniques. So I'm really excited to hear about that, and to you.
Yeah, great. Thanks very much, Jenny, for the introduction and obviously the invitation to this Tech Talk series. I'm very happy to be here, and thank you everybody for coming up to this talk. I'm Ryuji. I'm a Lee Kuan Yew Research Fellow at NTU Singapore, and today I'll be taking this opportunity to tell you a bit about the error mitigation, as Jane mentioned, trying to characterize the ultimate potential and limitation of quantum error mitigation. So, before even going to the second slide, let me just give you the brief sort of motivation and background how I sort of started thinking about this kind of thing. So, the error mitigation is the way to suppress the error, the noise effect that happens in the near-term quantum devices, like Nisk devices. And people have been excited about it and, trying to come up with the different protocols, then check if this actually works, and if it's not, then trying to come up with a new one. And we have now variety of ways of doing the error mitigation. But now it's a good time to think about this systematic understanding of these next series of error mitigations, because without that, we could not get the sort of solid theoretical understanding of the ultimate power of the error mitigation, and that also leads to the understanding of the ultimate capability of the Nisk devices themselves, which is one of the main questions asked in the community. And so one of the messages that I'm trying to send in this work is that error mitigation might have a very fundamental obstacle to use, and it might be very hard to make the useful computation possible. So I also heard from Jane that especially here in the Horizon computing, people are interested in the fault-tolerant quantum computation more, or at least toward it. So this might be actually I hope actually that the results from this work give you even more motivation to think about these fault-tolerant regime because there is actually the limitations that are fundamentally imposed on the error mitigation techniques in general. So this talk is based on these two references. So the first one is about introducing the general framework of error mitigation and discuss the consequence that we can discuss from that. And the idea of the first paper is that if we want to, give the systematic approach to the error mitigation, and first we need to sort of get the general framework on which we can talk about the characterization of the classes of the protocols that are in such a general framework. So this is about the first one. And the second one, we talk about the very important figures of merit that people should think about in the error mitigation, which is the sample costs, which is the number of the times that you need to run the Nisk devices to get some computational accuracy. And we get some fundamental sample cost that is required for the general error mitigation protocols. So to set up the stage, when I say Nisk devices, it means noisy intermediate scale quantum devices. And the idea of that is, of course, one of the ultimate goals in the quantum information science is to build the fault-tolerant quantum computation that is helped by the error correcting codes. But error correcting codes usually require a lot of number of qubits or very accurate gates, so it is very hard to implement. So this idea of Nisk devices is to use some much smaller devices which contains like a tens to hundreds number of qubits, and without diving into the complicated error correction scheme, and still trying to see if we can do anything useful with it. So nowadays, like there are many sort of people, academics and startup companies trying to see if the Nisk devices can actually give you the useful application of that. But I think that there's still a big theoretical question there. How one can characterize the capability of these Nisk devices, because there's no like a theoretical, like a solid ground that we can show that some useful advantage. So when it comes to characterizing the ultimate capability of such devices, one of the important aspects is the noise, of course, right? Because noise should be avoided by the quantum error correcting codes, but we are saying that the Nisk devices do not implement the error correcting codes. So we cannot just ignore that. So the question is, how do we counteract the noise effect even on the Nisk devices? Then how much we can deal with those error effects is one important factor of characterizing the capability of the Nisk devices themselves. So we are now focusing on what the capability of suppressing the noise effects on the Nisk devices. Then this is the idea of error mitigation. But before going to that, error correction is the idea to encode the quantum state and also the effect of the quantum gates into the higher dimensional Hilbert space. And we prepare the encoded version of the state and gates and apply some error correction at the end of it. So this requires many qubits and also requires adaptive online feedback control and making the stabilizer measurement and do the feedback operations and so forth. So this is quite hard to be implemented. On the other hand, so the error mitigation or Nisk devices do not want to do that. The idea of error mitigation is to run a given Nisk devices just many times and make measurements at the end and collect that measurement outcomes. Then apply some classical post-processing on the measurement outcomes to it and trying to extract the classical information that you were interested in. So like the expectation value of the Hamiltonian and so forth. This itself is a classical information. So as long as we can get out such a object function, then that should be fine. So this is the idea of error mitigation. So this typically does not require online feedback control. And as a resource-wise, what's happening is that error correction uses many number of qubits in sort of, considered as a space resource. But in the error mitigation, you trade the space resource with the time resource in the form of sampling cost. So here sampling cost again means that, so I said that error mitigation uses the Nisk devices so many times and take a statistics of that and trying to get the classical information that you were interested in. So the number of Nisk device runs is the sampling cost. So if this, then if you can see that, if you see in that, the sampling cost is a very important figure of merit, because if this is too much, then you cannot end the experiment in a reasonable time. And since you're trading this time cost with space cost, then now the time cost is really the question. The question of sort of like telling the capability of error mitigation. Okay, so to give you a more concrete ideas of the error mitigation, sort of as an introduction, it's, I think, good to give you one specific error mitigation protocol to give you the sense, and we are on the same page. So this is something called probabilistic error cancellation method. This is one specific error mitigation protocol known in the community. So let me introduce that. So suppose that your goal is to get the expectation value of some observable A. So this A ideal is this, the psi is the ideal state, the noiseless state. So you were interested in getting this expectation value with respect to the ideal state psi and observable A. A is a Hermitian operator. But because of the noise, like you have some noise effects that applies to the state psi. So instead, you will have the noisy expectation value. So the idea is trying to get this, the ideal expectation value out only using the noisy device. So how do we do that? So to do that, let me hypothetically consider this kind of action where we try to implement the inverse map of the noise, like E inverse. I mean, if we could implement this E inverse, then there wouldn't be no problem because you apply the E inverse and you will get the ideal state out and again measure the observable A. But the problem is that this E inverse is usually not even a physically implementable map. For instance, this is not completely positive. So the idea now is to try to simulate the action of this inverse map, E inverse. So to do that, let's now express this E inverse in terms of the implementable operations on the noisy device. So let's say there could be alpha, some set of operations. Then I would try to write this E inverse in terms of the linear combination of the basis operations that can be implemented on the device. And these eta are the coefficients, like real numbers, that are coefficient in the composition. Then importantly, this eta can be also a negative number. This is just a real number. But anyway, so if you can write it out, then this ideal expectation value can be sort of straightforwardly written in this way, where this A alpha is something that you can implement on your device because this beta can actually be implemented. If you further write it out, then I can just get the second equation. I just play around with this equation. But basically, this gamma now is the absolute sum of the coefficient. So remember that this eta can be negative. So I take the absolute value of that. Then I also introduce the sign factor of eta alpha. So sign is if eta alpha is greater than or equal to 0, it gives you 1. Otherwise, it gives you -1. So it just detects the sign of the real number. Then P alpha, I define it this way. So this constructs a probability distribution over alpha. As you can see, by definition, if you sum up this P alpha over alpha, then it gives you 1 by definition. And also it's greater than or equal to 0. So it constructs a probability distribution. So the question now is, with that, how do we again try to estimate this ideal expectation value? Then we will bring up now the technique known as a quasi-probability sampling technique, where we apply some basis operation B alpha at probability P alpha. Again, so P alpha was a probability distribution. And measure A, expectation, the observable, and get some outcome. And I will take this random variable here, measurement outcome multiplied by this gamma factor, which is absolute sum of the coefficient, and sign of this coefficient eta. And I repeat it so many times and take a statistical average. Then at the end, at least the sample infinite limit, it gives you the expectation value, the ideal expectation value. So by that, I say that this constructs an unbiased estimator because the expected value that you will get by this technique is the same as the expectation value that you were originally interested in. So this was kind of the operational way of doing it, but what's happening physically is that suppose that this dotted distribution is the one that you would get from the noiseless state, like ideal state psi. If you measure this A, then you might have some distribution. Then you're trying to estimate the expected value of this dotted distribution. But because of the noise, this distribution might be shifted towards some direction. Say, if you get a depolarizing noise, and it might just goes to the direction of origin. then what this probabilistic cancellation is doing is trying to shift this noisy distribution back to the original place, like that, but with the cost of the broadened distribution. So as you can see, the expected value of this, I call it the error-mitigated distribution. Then this error-mitigated distribution, the expected value of that shifts it back to the original expected value of the dotted distribution. But this is broader than the original one. Then this broadening happens because of this multiplication of gamma, basically. If there is a negative coefficient in eta, then that is picked up and gives you the larger value of gamma. So gamma is usually greater than 1, so it broadens the distribution. Then this is what's happening. So then basically, the sampling average is to sample from this error-mitigated distribution and trying to get the expected value of this broader distribution. So if you think about that, then the sampling cost you need to pay, essentially, to achieve this target accuracy is going to be proportional to the gamma squared, where gamma is, again, the sum of the absolute value of coefficients. And this is because this broadening happens because of the multiplication of this gamma. So this is how sort of you try to get the original classical information back, but at the cost of more sampling cost. But this is just one example of the error mitigation. Okay, so besides this probabilistic cancellation, there have been many error mitigation protocols proposed so far, like say noise extrapolation, where you try to boost your noise strength artificially and estimate the expectation value for each point of the noise strength, so that you try to extrapolate to the noiseless limit and try to guess what the noiseless situation was. Or virtual distillation was a recent proposal where you use multiple copies of the noisy states and apply some coherent interactions between them and run the experiment many times to get the pure portion of this noisy states. So this is a virtual distillation. Or symmetry verification is to detect the violation of symmetry that should be respected by the noiseless state. So on and so forth. Okay, so now seeing this zoo of error mitigation protocols, and these are fine, and the performance of each protocol was characterized on case-by-case basis. But then we can now ask the question, I mean, when should we stop this journey? Like, when should we declare that we are okay with sort of seeking the new error mitigation protocols? Like, where are we going for? What is the theoretical goal of finding the new error mitigation protocols? So these case-by-cases approach cannot answer that question, because once you propose a new algorithm, then you might wonder if there is another better algorithm. If it doesn't work, then let's go to the next one. But to get the fundamental limits on such a journey, and we need to have some systematic understanding, a general idea of error mitigations. And that is related to, again, the ultimate characterization of the Nisk devices itself. So this is sort of the motivation of our work. So basically asking, what is the ultimate performance shared by all error mitigation protocols? And to do that, we need to have some general framework for the quantum error mitigation on which we can discuss some quantitative argument. Okay, so this is sort of like a summary of our general framework, which is pretty simple. Okay, first of all, this refers to the ideal situation where you don't have noise. Then in this case, what you do is to make a measurement about A to the noisy state psi, and you get some distribution, and you try to estimate the expected value of this distribution. However, in the noisy scenario, you have some noise, so what you can pretty much do is to collect these noisy copies, maybe multiple copies of that, and apply some quantum processes on top of that, and get some estimate of the expectation value after measurement and also post-processing. I will make a note that these E1 to En, we call it the effective noise channels. This might be different from the actual noise channel that happens in the quantum circuit, but this is a map that connects the ideal state psi to the noisy states that are output from the noisy circuit. So after doing that, I get some, so this is the random variable. Yes?
Sorry, should we be assuming that that's a CPTP map?
Yes.
Okay.
Then you can, if you know the description of the circuits, like unitary circuits, then you can always come up with such a CPTP map that connects this ideal state and a noisy state.
I don't believe that's true, but okay.
So basically, this formally, if this E could have some inverse map of the unitary gate, and if you then you add the description of that noisy circuit on top of that, so
you're fixing the input. You're assuming that the circuit has a fixed input.
no.
Okay.
But this circuit, ideal circuit, let's say this can be constructed by sort of series of unitary. But instead of that, you might have some noisy circuit. So let's say this is a quantum channel. So formally, what you can do is you define this E as first like an inverse of the original ideal circuit. Then also apply the noisy quantum channel that describes a noisy circuit.
E is just operating on the fixed state psi at each point, and you don't care about what E would be if it was a different psi. You're just saying for each of the psi, like for some particular psi, I can fix that psi, and then all of the outputs I can relate by different CPTP maps applied to that psi. Is that correct?
So you don't fix psi in the sense that I also allow different input states on the ideal circuit. So if you input maybe the different input state, then you might have the different ideal output, say like phi. But this, if you input if you have a different input state in this noisy circuit, then you will also have the noisy state that is like E of the ideal state phi. So this E itself is not dependent on the description of psi, but this is...
That issue that E is being described as CPTP map when it can be non-Markovian noise.
So yeah, exactly. So like your noise might depend on the state you try to set as input, because maybe you warm up some component and that has a knock-on effect at multiple parts of the circuit.
Oh, I see.
So it's not always related by like states that are supposed to be orthogonal are not always orthogonal. So there's not always the linear relationship that you would expect.
In that case, right. Yeah, so in that case, that this E should be dependent on the psi. But I didn't consider that situation. Yes. Yeah, thanks for bringing it up. That's something that I didn't really think about deeply. And yes, so then after this quantum process, you output some random variable that serves as the estimate of this expectation value. Then you will construct some probability distribution. This is like error-mitigated distribution. And to understand the performance of the error mitigation, what you can see is these two things. The first one is the bias, that is difference between the true expectation value, this is the blue one, and the expected value of the error mitigated distribution. So this is like a systematic error part. And we can also see some indicator of how spread your error mitigated distribution is. So we call it the spread. As for now, like we define it as the difference between the maximum possible value and the minimum possible value. Okay, so this was a general framework, but we could say a bit more than that by taking a look at inside of this black box quantum process to help us classify more the error mitigation techniques. So some error mitigation techniques just have the property that they only apply the coherent interaction between the up to Q number of some number of the noisy copies, copies of the noisy states. So in that case, what's happening is you will have some quantum experiment that only takes in the Q number of noisy inputs. So like each of which constructs some POVM measurement. Then I have K of those. So these might represent the different experiments, and then each of it takes these Q inputs. So like if you just collect count the number of these copies, then this is like a Q times K, but I have Q inputs and like a K experiment. Then each experiment outputs some like a measurement outcome in some one round, then gives you some measurement outcomes I1 to IK. Then what I do is then apply some classical computation on top of it and declare some like a single shot estimate of that corresponds to the expectation value of this. Then I repeat this like m times, and I collect the sample from 1 to m, and I take the average over that. Then I call this EAM is the estimate of our the expectation value. So I call it QK error mitigation, which means that this Q is a number of inputs that can be coherently interacted, and K is the number of different experiments in this strategy. So these are some examples and how sort of like these fall into our framework. The one that I described, the probabilistic cancellation, is an example of like 1-1 error mitigation. Q is 1, K is 1, because I take in one copy of noisy state and apply the same experiment like many times. So that's why it's Q is 1, K is 1. On the other hand, the R's order noisy extrapolation, I use the R plus 1 different number of noise levels and collect the measurement outcome from these experiments. So I have, but each of experiment only takes like one copy of a noisy state. So this is Q is 1, and K is R plus 1 case. Then this R copy virtual distillation is taking this R copies of the noisy quantum states, then apply the coherent interactions among them and do the experiment many times and get the estimate. So this is Q is R and K is 1 case. Okay, so then how do we understand the quantification of the performance? So I already mentioned bias a little bit. So this bias is again the difference between the true expectation value and the expected value of the error mitigated distribution. And we will also have another error, short noise. This is a statistical error that comes from the finiteness of the number m, the round number m. So then you might have some statistical error delta on top of it. Then now the question that we want to ask is, okay, so the bias function is an internal function that's built in the given error mitigation protocol. Then we are interested in still to characterize this given error mitigation protocol then what you can still like discuss is how many rounds you want to use to get some computational target computational accuracy delta. So this I told you that I do this like this repetition n times. So like how many times you might want to do that? To discuss that, if you look at this half-degree inequality, where which says that the m samples ensure some like computational accuracy with success probability if this m is greater than this quantity right-hand side. Then this quantity, like I use like this delta EA. So this was a spread that I also mentioned in the previous slide. That is the difference between the maximum possible value and the minimum possible value over here. So in this way, this maximum spread is somehow connected to the round number you might want to use. And also, we are interested in characterizing the performance of the strategy itself. We will also take the worst case scenario and take the maximization over the observable and state like this. So then I call it the maximum bias and maximum spread and look at how these behave. Okay, so now the concrete question that we are asking is, what is the unavoidable maximum spread for given maximum bias? So again, the maximum spread is connected to the round numbers. And so that is the sort of operational number on the error mitigation, and how is that, how much should it be, how large should it be in terms of some bias function. Yes, so this is, okay, so this is like a main result of this first reference, basically. So suppose that you're given the arbitrary QK error mitigation protocol in our definition. Then this maximum spread is always lower bounded by this right-hand side quantity. So this spread must be larger than this quantity always. So let me sort of break it down a little bit. Okay, so first of all, this the right-hand side is represented by the distinguishability of the quantum states. Then this denominator has this d trace. This is the trace distance between two states. And this psi and phi are the states that are supported in this as a single copy. So this is like one small state right here. And you can consider this psi and phi are the ideal states, like a noiseless state. And you look at the possible noiseless states, then the difference between them. So this is the denominator. And I also have the maximum spread here, so numerator, and the maximum spread, the maximum bias is also in the numerator. In the denominator, I have the local distinguishability measure. Again, this is the distinguishability between two quantum states, but this is distinguishability only using the local measurements. So what I mean by local measurements here is that the measurements that correspond to this experiment, like each experiment. So I call these, define each experiment as a subsystems when I say local. They're basically only using the measurements in these experiment and how much you can distinguish between two states. I mean, this comes from the hybrid nature of the error mitigation, where everything quantum happens in the within the experiment, but after that you do some classical computation. So this kind of reflected in this measure. Then this phi tilde and psi tilde is a noisy state that is right after this effective noise channels. So this is like a big state over here. Okay, so like, well, what is this basically saying? So how do we interpret this? The first interpretation is that if when the noise decreases the distinguishability measure, I mean, making it hard to be distinguished, then the right-hand side increases. So then that leads to the unavoidable increase in the maximum spread. So this is a pretty like intuitive relation, but quantified in this way that connects this error mitigation performance in the left-hand side and also the information theoretic measure of distinguishability on the right-hand side. So this is one interpretation. You can also see this as a trade-off between the maximum spread and the maximum bias. So if you are okay with a larger bias, then the right-hand side decreases a little bit. So you might be able to realize a smaller maximum spread. Okay, so this was sort of a, one result, but a bit abstract. So what is the application of this idea? So let me bring up one theoretical application at least. So this is related to, okay, like I guess I forgot to mention in the previous slide, but one question that we could ask is, can we say some optimality argument for some specific error mitigation protocol? Right, because if you can say in some sense that this is optimal, then you're kind of good theoretically. But to say some optimality of the specific protocol, we need to have the understanding of the general error mitigation protocols. So this was also the motivation of our work, and this gives you at least one way of looking at this kind of optimality argument. So to do that, let me actually also bring up again the probabilistic cancellation method, which is the example of 1-1 protocol. Q is 1, K is 1. And this is a reminder that I decompose this inverse map in just like a linear combination way. And I define a gamma as the absolute sum of the coefficient. I can also consider the optimized version of gamma optimal, which is optimized over also the basis operations. I mean, technical side aside, this is gamma basically. Then you can see that this maximum spread for the probabilistic cancellation is gamma because this contributes as a the scaling of scaling factor. So this was also studied in the previous work, like that. So if you take the specific noise channel, like a local dephasing noise, for instance, then I can calculate this gamma optimal exactly. So this gives you the maximum spread for the probabilistic cancellation. So this can be written in this way. On the other hand, now let's forget about, for now, the probabilistic error cancellation and look at our general bound. So our bound implies that we also, let's look at the unbiased version of a bound, and also Q is 1, K is 1. So unbiased 1-1 protocol. This also constructs some family of the error mitigations. Then we apply our bounds like that. And after some calculation, you can get this lower bound. Then this lower bound, as you can see, coincides with each other. So this lower bound is achieved by this probabilistic cancellation method. So by that, we could argue that this probabilistic cancellation is optimal for this scenario, at least in this specific sense. So this is kind of a restricted setting still, but this at least gives you like one approach to discuss such an optimality question. Okay. So then I've been talking about this maximum spread as sort of figures of merit, like important figures of merit. But now, that was the content of the first reference. But let me now also point out some subtleties of considering this maximum spread. So if we remember back our original motivation, we were primarily interested in the sampling number that we want to use. And especially if we want to get the ultimate fundamental limitations imposed on the error mitigation, we want to have the lower band of the sampling number, like how many samples you must use to achieve some accuracy. So this maximum spread is one indicator of that. but this was supported by the half-length inequality, but the logic is kind of opposite there actually, because half-length bound gives you the sufficient number, the round number m. So if you use this round number m, then you can get this computational accuracy. Whereas it would be nicer if we can get the opposite, like a necessary sample number. You have to use this sample number always to achieve this computational accuracy. So this is one point. We are not perfectly satisfied with this figures of merit. And the second point is related to the first point, and the gap between the estimate from this half-length bound and the required samples can be actually fairly large, especially if you think about the error mitigations that involve the nonlinear post-process. So to think about that, let me also bring, discuss that error mitigation typically works as follows. So you have some set of measurements as observables, like OI, maybe like Pauli measurements or whatever. Then you estimate their expectation values first for these observables, and you have some number, set of numbers, that is the expectation value of such observables, and you apply some classical post-processing on the estimated expectation values of these observables. Okay, then this post-processing function f, if this is linear function with respect to the expected values of these observables, then the order of taking the sampling average doesn't matter. Like you can take the sampling average before and after in either way. But if this f is highly nonlinear, then you have to first take this expectation value, then apply this function f. So if you want to characterize that in our framework, then this corresponds to the scenario where this number of experiments k is very, very large, because this one round has to take very many, has to take into account all the samples to estimate these expectation values, then that leads to the very large k. So at the end, what's going to happen is you have the very large maximum spread, but it might give you the very sharp peak in the distribution, and that gives you the error mitigated estimate. But this, if that happens, then our previous result might give you the imprecise estimate of the required sampling cost. So we need to have a different approach to take care of that problems. And this is what we're going to do. So the idea here is we just forget about round number, then just focus on like a single round number, but take every samples required for the error mitigation in this picture. I don't consider repeating the measurements or anything, but just take all the samples used in the error mitigation in this way. So now I have 1 to n copies of noisy states. Then if you write it out in this way, then the question reduces to what is the number n? What is the lower bound of this number n? So this corresponds to the lower bound of the sample number. And this doesn't have the problem with the nonlinear post-processing or anything, because post-processing is all encompassed in this PA, so like this black box. Okay, so this is our goal, and again we can discuss the performance of the error mitigation by now using the underlying distribution of this random variable EA. So, since we declare that this is the end of the experiment, we just don't repeat anything. But this is itself is a random variable, so you have some underlying distribution like that. And using this underlying distribution, we can discuss 2 performance measures. The first one is accuracy and success probability. So accuracy delta is the deviation from the true expectation value. Deviation from the true expectation value, and how much the probability you can achieve such a accuracy. So this combination of accuracy and success probability, this is a very operationally motivated figures of merit of the error mitigation. But the second approach is to use, again, the idea of bias. This is a systematic error again. And also some error that, comes top of it. But we are not going to use the maximum spread in this case because maximum spread is a very crude, measure of error. Instead, we're going to look at the standard deviation. Standard deviation gives you much better the sense of error that happens in this error mitigation. So that also takes into account the case that we showed in the previous slide. So these two are, possible performance measures. And we're going to have such a sample lower bound for each scenario. So the first scenario, to set up the stage, we're going to quantify the performance by how well the protocol can estimate the expectation values for some set of target observables. So these are the observables for which the error mitigation is designed to work, designed to give you the good estimates of, and also the set of ideal states, S. So this is, again, the set of states for which the error mitigation is designed to give you the good estimates of. So then you can characterize the first framework by looking at the probability of having your estimate within the accuracy delta. And the probability of that should be greater than 1 minus epsilon. This is success probability for all the target states and target observables. Then we can get this kind of lower bound of the samples. This is kind of complicated, but the message is kind of similar. So if you look at the denominator, this is in some sense, again, the distinguishability measure or the distance between the quantum states. So this is F is a fidelity measure. So if basically this noise E, if this noise E gives you the worse distinguishability, then this denominator again diverges or increases, and it gives you the larger sample cost. So this is an unavoidable sample cost you have to pay. And you can look at the various sort of parameters here, success probability and the accuracy, and this also contributes to increasing the right-hand side to give you the more sample cost. For instance, if you want to get a better success probability, then you need more samples. If you want the better accuracy, then again, you need more samples. This kind of indication can be derived from this. So now we got the sample lower bounds, which was the original interest of us. And so this then also works for the error mitigations encompassed in this way, in this framework. The second setup is the bias and the standard deviation. Again, so the bias is this, and the standard deviation is the standard deviation of the error mitigated distribution. And one advantage of looking at this framework is we can separate out the systematic error and the statistical error in this way. But it might have a drawback if you are interested in the high success probability, in which case you might want to use the first framework. But anyway, so this also gives you this kind of sample lower bound. Again, this looks complicated, but the denominator is the same. Again, if the fidelity goes to 1, then this gives you the larger sample cost, and so forth. So this one can be also discussed further in terms of, again, back to this optimality question. In the previous framework, we were able to get kind of clean optimality argument. In this case, it's difficult to get such a clean matching bounds and so forth. But at least if you look at some the scaling with respect to some parameters, and we can see that the scaling matches. So again, look at the local dephasing noise. And if you look at the high noise regime, then the lower bound, the right-hand side of that, and if you look at the dependence of this error, no noise strengths, then this lower bound, you can show that this lower bound scales like this. But this scaling can be also achieved by the probabilistic cancellation. So again, in this way, in this sense, you can sort of see some type of optimality of the probabilistic cancellation. So now let me apply our ideas to some scenarios which where we apply that to the circuit that is that consists of the layer of the unitaries. So like I have the number of L layers of unitaries, and that suffers from, let's say, the local depolarizing noise. And with some strengths gamma, like here. And your task is to suppress the noise effect from this local depolarizing noise by applying some error mitigation protocol. And I am also allowing ourselves to use additional operations inside the circuit, the lambda and xc. Then our technical assumption is that they are unital channels, so that map maximum mixed states to maximum mixed states. So this is our assumption. In this situation, we can show also the number of the lower bound for the samples that you need to use to get some computational accuracy in the two setups that I introduced. So these are, again, a little complicated, but the message here is that now if you look at the scaling with respect to the number of layers, L, then the right-hand side increases exponentially with respect to the number L. So this is the circuit depth. So, which means that you need to use the exponentially many number of samples to do the error mitigation in general. So this intuition was kind of shared, I guess, in the community for a while, but then this was seen for this, number of specific error mitigation protocols. But if you want to, state that in the general fashion, and one possible way of, approaching that is to set up this kind of general framework and get this kind of unavoidable scaling. And that applies to the general class of error mitigation protocols. So this gives you the fundamental obstacles to apply the error mitigation because you need to use many samples. So so this is kind of one observation that we can draw from this. Okay, so this is the end of the talk, so let me summarize briefly what I talked about. So again, our motivation was to get some ideas of the systematic understanding of the general class of error mitigations. To do that, we first introduced a general framework for the quantum error mitigation, and within that, we discussed some optimality argument for the specific error mitigation protocol, probabilistic cancellation for some certain scenario. And we pointed out also some subtleties of using the specific figures of merit used in the previous discussion. And we come down to the sample number, the necessary sample number that we need to use, and derive the lower bounds for such a sample numbers required for the general error mitigation protocols. And as an application, we showed that the mitigating errors in this layer circuits requires exponential number of samples with respect to the circuit depth. So as an outlook, I think in a broad sense, I hope to see more progress along with this general understanding of the error mitigation, and that would also lead to the general understanding of the power of Nisk devices. And there's rapid progress recently. There's recently one paper, and this week also extended and improved our results in some sense. So I hope to see those results more. And when it comes to the specific sort of outlook and the future research that comes from this work is first to characterize when our lower bounds can give good estimates. So we set up some general lower bound that applies to the wide class of error-mitigations. So we do not expect that this bound is always good it gives you the good estimates for the specific error-mitigation protocol. Because if you're interested in a specific error-mitigation, then you better just analyze it specifically. But it is still interesting to consider how tight our lower bounds can be, and when our lower bounds give you a good estimate, like the probabilistic cancellation example, and identifying these regime may be interesting. And also maybe making our bounds a bit more computable. We have several types of bound, some of which may have difficulty to actually compute things. So if you could get the alternative versions of that, that might give you different perspectives. Or characterizing a relation between the noise pre-knowledge and the required samples is another important problem, I think. So the probabilistic cancellation, if you want to get this unbiased estimator, then you need to know the description of the noise. So this is usually a hard thing to do. So what is a precise relation between some type of knowledge that you already have in the noise channel, and what is the cost that you have to pay with respect to such the obtained information about the noise? So that is, characterizing that quantitatively would be an interesting problem. And also, finally, what is the physical significance of that? In the second paper, we also discussed the extension of it to the thermal noise, and consider, then get the observation, something like if you want to get some computational results out, then you need to pay, the sample number you need to pay is related to the dissipated free energy of the system. So to get more connections to the computational size of the ideas and the underlying physical system, in terms of, say, mitigation, error correction, that would be also an interesting problem. Yes, so that's all I wanted to say. Thank you very much for attention.
You mentioned, I have a question.
Yes.
Do you mind showing the slide with the layered circuits? So the L that the circuit depth is basically the number of times you're repeating U1, U2, U3. It's just but each time is the same circuit. Is that correct, or is it different subsets of the circuit?
You can use a different unitary. So there's no restriction of the set of unitaries that you use in each time. So yeah.
But what's interesting is that the number of samples you actually need only depends on the depth of the circuits. Is that correct?
So this does not say that the actual number that you have to use is only dependent on the depths. This is just a lower bound that we were able to get, and that is expressed by the circuit depths. And the recent progress that put out in this week was also looking at the number of qubits in this circuit, and that should also grow exponentially with respect to the number of qubits as well as the depths. So this is basically, it's a matter of how good your lower bound can you could get. In their work, they looked at the sort of worst case scenario, one scenario that is tailored for their purpose, and you can construct some situation in which you need to have the exponential number of samples with respect to the number of qubits as well. So it's, I think in the practical, in a real setting, it's highly possible that also depends on not only the circuit depths, but also number of qubits and maybe other contributions as well.
Thank you.
Thank you.
I have two questions actually. So the first one is, it seems like the error mitigation protocols you talked about made use of the fact that you know E, you know the error map.
So in our analysis, and if you want to actually compute the lower bound, then you need the information of the error channels.
But generally, you don't know what the error channels are, right? So what you might have, you might be able to, for example, have some promise on the norm of an error map or something like this, or like the diamond norm between the two operators or something like this. But it seems like a question that you have if you just want to run this on practical devices, real Nisk computers, is you don't necessarily know the errors. Right. Like the errors are definitely not what theorists think their errors are. So how many samples do you need in that situation? Are you able to say anything about that? Because you have the problem of, dealing with the noise map as well.
Yeah, so that's a great point. And first of all, if you're given some error mitigation protocol and interested in the number of samples you want to use, you have to use, only using that, for using that error mitigation protocol, I think it's better to just analyze that specific error mitigation itself, because using our bound is quite generic. So it's kind of getting that,
Sure, but it seems the fundamental problem is you have some Nisky computer that you want to run stuff on, and you get to do many samples, and you want to infer out of that what the correct value is that you're trying to estimate from the device, right? What the true value of the observable will be for a noiseless device. That seems like it's a single problem.
Yes.
That it's not dependent on protocol or anything.
Right. Yeah, in that case, that's a case where our bounds can be useful. But back to your question, we still need some information about the noise. So that was the assumption that we had. And so we probably need to, if you're just given a noisy device, you might want to do the process tomography type of thing first and calculate those.
Sure, but process tomography is exponentially expensive.
Yeah.
To do in every circumstance.
Yeah. So we also have the bounds that are looser than this, but somehow could also estimate in the quantum computer, like without knowing the description of the noise. Okay, there's a trade-off between how good the bound is and that experiment itself also might be a hard problem. So actually estimating this lower bound requires more research. This is also related to one of the open questions of bounds are easier to compute in the sense of computationally resource and also you're in your sense, given a noisy device, and what is the way of estimating that without really knowing the noisy information. And one approach, again, we gave is the alternative bound, but you can also ask how good it is and can you get a better bound for that. So.
The other question I have was the way you set up the problem initially with taking many copies of the state and having some error map applied to them. That seems to be, essentially a metrology problem. But yet you don't seem to be using any of the tools of metrology. You don't seem to be using Fisher information or Grimoire bounds or anything like that. So I was just curious for your thoughts on that, whether there was a reason to not view it from that direction or...
Yeah, precisely. So at the same time that we posted in the second reference, there is another paper that came out, and that is the paper that precisely took your intuition and looked at the Fisher information of the noisy states, then get the lower bound of the sample number with respect to the standard deviation of the distribution, our second setup that we discussed in the second paper. The current difference between that and our work first would be that they only looked at the unbiased case, so unbiased estimator. So this is kind of a big restriction because most of the error mitigations actually are biased. So our work takes into account that, but their bound would probably give you the better, like a lower bound in a numerically. That's like one trade-off. And also the use of the standard deviation of the estimator, it probably usually gives you the good sense of the error, but this is still just a standard deviation. And also in the second framework, we didn't consider, they also didn't consider the repeating the measurements many times. We just like collect all the number of samples at hand, then apply error mitigation once and get random variable and look at the standard deviation of that random variable. So this standard deviation might give you somewhat imprecise error of the protocol sometimes, depending on the distribution that you actually get. So that was taken into account that in our first framework where we can set the arbitrary success probability and the accuracy delta. So yes, the quantum efficient information and extending those ideas to remedy those problems would be an interesting open problem. So like combining these two results together and resolve that problems.
Any more questions?
I guess I kind of a sort of open-ended question. Like, do you mind going back to the slide with the first your result with the theorem on the bounds on the I think this lower bound samples, where you have like before that I think. Yeah, this one here. This is very interesting. Yeah, like so it's like local measures at the bottom and then just the trace distance on the top. And then you have to, sorry, do you mind scrolling forward again to the other one? Yeah, this one. So, do you have any thoughts when the noise maps are like Gaussian? Like, I'm trying to see if you think that there's like some relationship with like the covariance of the noise maps. Sorry.
I haven't given much thought to it. So maybe you were thinking about the bosonic system?
Yeah, like if you have like thermal noise and then, it's like mixing with the reservoir or something. And if you can draw intuition to, because you have like noise, local noise in those channels, right? And then because your theorems is like, there's like distinguishability in like local measurements. And so I was just trying to see if like you have thoughts on whether there's a relationship to the like covariance matrices of the noise channel and things like that.
Yeah, that's a good question that I didn't think about too much. I guess, especially I guess if you also consider there's a phi and psi, also as a Gaussian state, for instance, then okay, the calculation of fidelity of the Gaussian state, yeah, it should be computable. So this is also related to like the computable bounds type argument. Like sometimes you are able to compute, and like that might give you the example in which you can compute this the denominator. The relation to the covariant matrix. I don't have the exact formula for that, but I mean, especially if you just like consider the Gaussian state and the Gaussian noise, then I wouldn't be surprised that there is a relation to that. Yeah.
Thanks.
Yeah, thanks.
Any more questions? Okay, and then I have one or two. Actually, so they had us on the first slide with the bounds, with the distinguishability, the trace distances of the two different states. Yeah. If I'm trying to understand it, is the bound coming from the fact that the expectation value of the observable A
it is in some way a way of discriminating the two quantum states.
Yes.
So it's in some ways giving me information that discriminates the two states.
Yes.
So is my bound telling me that is sort of like coming fundamentally from the fact that you can't discriminate the two states to a higher degree of accuracy
Yes.
than the noisy
Yes.
intermediaries?
Yes.
Is that what it is?
Yes, yes. So actually, like this question started from the very naive question by saying that, okay, quantum error mitigation mitigates error effects.
Yeah.
So does that actually help us to like distinguish two states, right? Because the error is mitigated. So can we actually like distinguish these states like better? I mean, no, right? Because like all we do is physical operations. So there should be the restriction there, which is the data processing inequality. That's a fundamental one. But error looks like mitigated in some way. So there should be some trade-off between, the fundamental restrictions put by the data processing inequality, then that's how you can formulate this kind of relation. Yeah.
Does that in that case tell you about how you can tailor your error mitigation protocol to the observable A? Like presumably maybe I should be like, if I'm doing a probabilistic error correction, maybe I should only be correcting error in subspaces in which A has large support or something like this.
So if you want to get, okay, like we also have a bound that is dependent on the observable A. Yeah, so, and this is sort of, one technical side to get the trace distance that we also need to take a maximization over. So like if you want to achieve this bound, then you might want to consider such an observable. But if you are just given a specific observable, then you also get some similar bound for that observable. Yeah.
Okay. And the metrology came up. Metrology being very interesting, actually. There's results in metrology which says that any kind of noise destroys the quantum advantage very quickly. Mm-hmm. I'm just wondering if I can sort of like see it in this framework almost. If I had like a GHZ state, and there was I get a metrological advantage out of that, but if I start to decohere the superposition in any way, like the entanglement between the 0, 0, 0 and the 1, 1, 1, then immediately my advantage is gone. Yeah. I'm wondering if you can see some of those kinds of things again here.
Yes. So the example of GHZ state is precisely what we use in the proof of showing, that's why we talked about the dephasing noise, when we discussed optimality and stuff. And the idea is pretty much the same or similar to each other. Noise decreases your information, and information that leads to more cost. The idea is this: how to characterize this information. If you look at the metrology type setting, that's a quantum information, also the quantum Fisher information, but you want to use a Kramer row, so you kind of have to use the variance measure, and also unbiased case is usually better one to look at. Then distinguishability, it's like, I would say it's the different way of looking at the loss of information, but you can play around with it a bit and you can get a bit more extended scenario. So that's why I said, right, replying to Joe's question, combining them and sort of like extract the lost information more precisely might give you the interesting results too. Yeah.
Okay. Good. Thank you very much, Ryuji, for giving a talk. It was very interesting.
Thank you. Thank you very much.